With that, I'd like to do a quick introduction of Stephen, and he'll go into a little bit more detail in his presentation. But Stephen Barrett is with SmithGroup, and he has 13 years of design experience in fire protection, fire alarm, building code, and life safety. We're very excited to have you here with us today, so thank you. And he also has and he also teaches plumbing and fire protection design at IIT. So again, thank you for your time, and I'll let him take it away.
Absolutely. Well, thank you, Liz, and hello to everybody. Let me start sharing my screen. Hopefully that all looks good. So yeah, today we're going to talk about fire and smoke dampers, duct detectors, and smoke control. So just to introduce myself, like Liz said, I'm Stephen Barrett. I'm a fire protection and life safety engineer at SmithGroup. And because I work at SmithGroup, which is an integrated architecture and engineering firm, I'm not a plumbing and fire protection engineer. I know that may have been confusing with my intro. I do teach the fire protection portion of that course at IIT, but I'm actually a holistic fire protection engineer. So yeah, I do sprinkler systems, but it's more so what I focus on is the multidiscipline collaboration, like doing code and life safety challenges with architects, or most importantly for today, working with mechanical engineers to determine when and where fire dampers and duct detectors are required. I get that question a lot, so happy to share all that information with you all today. So just a little pop quiz. We actually have a poll question for this. So you see here on the screen, I've got 1 hour fire rated construction. That's 5/8 inch jip on either side of a metal stud. That's a 1 hour rated assembly. Below that is 2 5/8 sheets on either side of the stud. That's a 2 hour configuration. And then CMU block, that's 8 inch nominal thick, is typically also 2 hours. So my question for you all, is this a firewall, a fire barrier, or a fire partition? So I don't know if you've started that poll yet, Liz.
Yep, it's going. We'll give you guys just a couple more
Cool,
seconds. About half of you have responded.
cool. Okay, kind of all over the board, but I'm glad that most people said depends. That is a fantastic answer. So if we look at the next slide here, so a firewall, now given the sections you can find in the International Building Code, IBC, firewalls are in 706, 707 for fire barrier, and 708 fire partition. All these require a fire resistance rating. All of them require penetrations to be sealed with an approved fire stop system. All require duct and air transfer openings to be protected with fire dampers, unless exceptions are met, which we'll get into. So what's the difference between all these? I ask rhetorically. So you might be thinking, why are you asking me this question? This is architecture stuff. Well, the reality is a lot of HVAC engineers don't really know when to put in fire and smoke dampers. And in fact, a lot of architects don't really understand the different partition types that I just mentioned: firewalls, fire barriers, and fire partitions. So this leads sometimes in projects, we're putting in fire and smoke dampers where they're not required. That's extra cost, that's extra maintenance. Or on the other side, we might fail to put them in where they are required, which could set up a potential life safety hazard. So why learn this stuff? Because as professionals, we owe it to our clients and the building safety, the occupants of the building, to trust in our expertise. So before we get into these different partition types, let's just quickly review some of the basic fundamentals. So a fire damper is the simplest and the cheapest of the different damper types. What it does is it prevents fire, typically in the form of hot air and gas, from passing through ducts and air transfer openings. So how does it work? Typically there's a fusible link, so that's a small piece of metal that melts at a relatively low temperature. And when that piece of metal melts, the blades in the duct drop. Usually melts 50 degrees above ambient, but not less than 160. So in the 125 to 160 range typically. And when that melts, you can see in this kind of ridiculous graphic that as the flames are shooting through, the damper closes, prevents fire from passing through, and that forms the fire damper. Fire dampers come in 2 flavors, hour and a half, 90 minutes, or 3 hours, 180 minutes. And anytime you're penetrating a 1 or 2 hour assembly, specify a 90 or 1.5 hour damper, and then use 3 hour dampers for 3 or 4 hour rated assemblies. These could have an electronic type of actuator, but typically it's fusible link. That's why these are the cheapest and easiest to install. Now, a ceiling radiation damper is kind of a special type of fire damper. It operates on the same principle of a fusible link melting and the damper closing. But these are pretty specific. You'll typically only see these in fire-rated corridor ceilings. Now, moving to smoke dampers, these are a little bit different. They're not quite as simple because they're detecting smoke, not heat. So a simple piece of metal that melts is not going to work. Instead, it requires a smoke detector and an actuator to activate the damper and close it off to stop that smoke from passing through. These are required to be minimum class 2 leakage rate, which I've provided here in the chart. That's 20 CFM per square foot at up to 4 inches water gauge. And then beyond that, you can see in the chart, there's higher requirements for the higher static pressures. These are higher costs than fire dampers. They're more complicated because they require actuators, they require smoke detectors. So they're a little bit more complex. Then finally, a combination fire and smoke damper is just what it sounds like. It's a combination of the two. So it both prevents fire and smoke from passing through. And really the difference is that it has both means of detection. So it's typically a heat responsive element that would detect the temperature, also a smoke detector. And if either one of these detect heat or smoke, then the damper is force closed with the actuator. So again, these are higher cost than a fire damper.
Stephen, we had a question that I think would
Yes.
fit well in. What's the difference between a static and dynamic fire damper?
Yeah, I was going to include that. So static, well, I guess we'll start with dynamic means that the damper is able to close under flow conditions. So you should pretty much always be specifying dynamic dampers, because otherwise, if you specified a static damper, it's only going to be able to close with no airflow. So if your system was operating, we detect a fire, either the fusible link melting or the smoke detector detecting smoke, and the actuator or the spring starts to close, there may be so much pressure and velocity from the air flowing through the duct, it prevents the damper from closing. So typically it's best to always specify dynamic dampers. That's the cost difference is pretty marginal. And we'll actually get into a little bit of whether or not those units will be shut down when these dampers do need to close. So hopefully I answered the difference between the two.
Thank you.
All right. So what you all came to hear, different partition types. I mean, this is really important because you all said depends on the answer to that question, right? So the requirement whether or not you need a smoke damper depends on what type of construction is being penetrated. It's not simple enough to say, well, it's 1 hour, so I don't need a damper. And if it's 2 hours, I do. That's not true. It's an oversimplification, and that could lead to some of the errors we talked about at the beginning. of either over-specifying dampers when you don't need them, or even worse, missing one and having a potential life safety issue. So today we'll review the 5 types of fire-rated construction described in the IBC and the 3 types of smoke-rated construction. And again, we'll use the 2015 IBC, which is probably the most common in adoption right now. It might be trending towards 2018. They're on 3-year cycles, but these requirements are going to be pretty consistent throughout 2012, 2015, and 2018. And NFPA 90A we'll touch on a little bit. That it's required for a lot of government and federal projects, and it's sometimes adopted by local jurisdictions. So we'll mention a couple of the key differences later on. So the few of you that said firewalls on the poll question, pay attention. It's not just semantics. It really is important to differentiate these different types. A firewall is a special type of construction. It's actually pretty rare. It's used to divide a building into separate buildings. It's the most restrictive type of fire-rated partition you can have, or fire-rated assembly is a better word. And most of the time, they're not this extreme. So try to avoid using that term firewall. And I'll admit some architects will use it incorrectly, but if you do have a firewall, it allows you to separate the 2 buildings and treat them as separate buildings. So they can have 2 different construction types. They can have 2 different calculations in terms of allowable heights and areas of the building. It's basically 2 separate buildings. Why they're extreme is because firewalls are typically 3 or 4 hour rated, which is really high, and they're structurally independent. So either the wall itself is independent, not tied to either building, or you may have 2 back-to-back walls that are tied to their respective buildings. But it's constructed in such a way that one building could completely collapse and the other building will stay standing. That's how extreme a firewall is. Now, if you do penetrate a firewall, provide a fire damper. Typically, it's going to be a 3-hour fire damper. If you do have that structural independence where you have back-to-back walls, then provide a damper in each structurally independent wall. But important to note that you cannot run a duct or air transfer opening through a firewall on a property line. Not at all, period. You can't do it. If 2 buildings are separated with 0 lot line with firewalls, you cannot penetrate them at all. And I've got some code sections cited here, so you can find the firewall requirements in 706 of the IBC. Now, a fire barrier, if you guessed this on the poll, we'll give you half credit. This is probably the barrier you'll see most on your projects. It's in exit passageway, atrium boundaries, fire area separations, occupancy separations, hazardous area separations, like a mechanical room, for example. And the ratings do vary, but they're typically 1 or 2 hours. Again, just like firewalls, this is going to seem like a theme here. Provide a fire damper when a duct or air transfer opening penetrates a fire barrier. But there is an exception, one that probably a lot of you know, and it goes like this. If the fire barrier is 1 hour rated, so it can't be 2 hours, 3 hours, max 1 hour, in a fully sprinklered building with a fully ducted system, so that rules out air transfer openings, then you can omit the fire damper. But key distinction, you cannot use flex ducts as part of your system. It's obviously very popular, very common on projects to have flex ducts. And this is something that gets missed a lot on projects, but technically you must provide, or let me rephrase, this exception does not work if you utilize a flex duct as part of your system. Another important note is that you cannot run ducts or air transfer openings through exit passageways, or stairwell enclosures. Period. Not at all. You can't do it unless those are specifically serving the stair. So you cannot utilize stairs or exit passageways as pass-throughs for your ductwork. So again, on that exception, important to note, will not apply for air transfer openings and requires a fully ducted system, no flex.
There was a comment in the questions that the latest version of IMC 2021 allows for flex ducts now.
It does. All right. Well, thank you for sharing that. Yeah, so I would say that I don't know of any jurisdiction that's adopted 2021 yet. It might be a while, but you know, up to you if you want to utilize something like that. But I think technically that would be an equivalency. That'd be something you would definitely want to run past a code official if you want to utilize, you know, that future code, which maybe the jurisdiction will ultimately adopt, probably. But they could change that section. You know, when jurisdictions adopt codes, they often have amendments. So it's not a guarantee that they're going to adopt that section, but yeah, thanks for sharing that. I actually didn't know that. So good to know.
And then there was one other clarifying question, which I think I can answer.
Yeah.
But the clarifying question is, you can't use flex ducts in any portion of the system, correct? Or is it just through the okay?
Any portion of the system.
Not just through the fire barrier.
Mm-hmm. Yep. But yeah, thanks for sharing on the 2021. I'll have to make an amendment to this presentation for that. Now, fire partitions are the third and the least rigorous type of assembly. And they're typically 1 hour rated. And you'll find these often in corridor walls in residential buildings or non-sprinklered buildings. Tenant separations in multi-tenant buildings like open malls, and walls dividing dwelling units in multifamily housing. But a lot of buildings are fully sprinklered. So in a lot of occupancies, excluding residential, the requirement to rate corridors goes away. There is no requirement. So in section 1020, which is the corridors section, and in table 1020.1, you'll find the requirements for rating of corridor walls. And just like the other two, the baseline requirement is to provide a fire damper. The exception for fire partitions is a little more lenient. It's similar to fire barriers where 1 hour or less, which it's pretty rare to have a fire partition that's more than 1 hour. Fully sprinkled building and a ducted, not air transfer opening. And then you can omit the fire damper. Otherwise, if you do have a non-sprinklered building or you have an air transfer opening versus a ducted penetration, then provide a 90-minute or 1 1/2 hour fire damper. Now, shaft enclosures. Most of you probably are pretty familiar with shaft enclosures, but it's important to define what exactly a shaft is. It's a special type of opening between floors. So typically we cannot have openings between floors. Typically the floors have to be continuous from exterior wall to exterior wall. Obviously, we have to have stairs in our buildings for egress. You know, we have to have elevators for accessibility. So we do have openings in our floors, but those are typically required to be protected as shafts. So you are all probably familiar with running your ducts through shafts. And the typical requirement is for 2 hour rating of shafts. It is only 1 hour if connecting 3 stories or less. And shafts are typically continuous to the roof. They're typically start at the slab and go all the way up to the roof, but they are permitted to be open to a room that is of similar use of the shaft and protected like a shaft. So it could open directly into a mechanical room. And the most important thing here though, and you might have already known this one, if you penetrate a shaft, provide a fire and smoke damper. So a combination fire and smoke damper when penetrating the shaft. So that's when entering or when leaving the shaft. Now, horizontal assemblies, this is kind of a fancy word, but it refers to floors, floor ceiling assembly, or roof ceiling assembly. Now, generally speaking, ducts cannot penetrate horizontal assemblies. Just as a general rule, your ducts need to run in shafts. But there are a few cases when a duct can penetrate a floor, for example. So we'll get into those. But why it's floor ceiling versus floor, you might be wondering what's the difference there. The difference is that the ceiling is required. It's actually part of the assembly that helps it achieve its fire rating. So like we saw at the very beginning, we can use gypsum to get fire ratings. So in the case of a floor ceiling or roof ceiling assembly, there's going to be a layer of gypsum, and that gypsum is required. It actually is part of the assembly sandwich, if you will. By contrast, a floor assembly is just that. It's just the floor. Typically it's 6 inches of concrete or so, and that's all you need to get your fire rating. So if there is a ceiling, that is not providing any fire rating. It's just there for building construction purposes, for acoustics, or for maybe it's a plenum, maybe it's hiding utilities. So important to be able to differentiate between a floor assembly and a floor ceiling assembly. Now, first thing to note on this graphic, and the slide is the graphic on the right. That's called a through penetration because the duct is penetrating fully through the floor. And so if the floor you're penetrating is fire resistance rated and the duct is connecting only 2 stories, provide a fire damper at the floor line. That is permitted. There are also, in residential, for small ducts 4 inches or less, you can penetrate up to 3 floors with no damper required. That are fire resistance rated floor assemblies. Some buildings, though, have non-rated floor assemblies based on their construction type. So in those cases, you're permitted by code to penetrate, to connect 2 stories without having any damper, or to connect 3 stories, but no more than 3, and having fire dampers at each floor line. If you don't meet any of these requirements, you must run your duct in a shaft. So that's why I said earlier, basically you should always be running your ducts and shafts, but there are some specific allowances in code to run a duct through a floor, and possibly with a fire damper at the floor line, depending on whether or not the floor assembly is fire resistant rated or not. And then at the bottom there, I note that I2 and I3, which is hospitals and prisons, these aren't permitted. Did we have a question, Liz?
Yes, but I can wait till you're done with this before we go into smoke.
Okay. And so by contrast, a through penetration, like I said, runs fully through, but a membrane penetration doesn't go all the way through. It penetrates into, so think of into the membrane, but not fully through. So you can see in this graphic here that there is a duct that penetrates into the roof ceiling assembly. So you can see on the very left of this graphic, there's a big circle that says fire resistance rated assembly. It's a horizontal assembly. So this is the case where I talked about that sandwich. This is roof ceiling because the roof and the ceiling itself are all part of that assembly. You need all of it to get your fire rating. It's not just the roof itself. It's not just the ceiling itself that gives you the fire rating. So in this case, that duct is penetrating just the one portion of the ceiling there at the bottom. So code permits a ceiling radiation damper to be provided. In other cases, if you penetrate a membrane penetration, it must be run in the duct. Or must be run in a shaft, excuse me. Did you want to ask the question now, Liz?
Yeah,
Or?
I think so. There's two actually.
Okay.
So I think pretty early on in the presentation, you mentioned temperature ratings. If it's
Mm-hmm.
not less than 160 degrees Fahrenheit,
Mm-hmm.
then the temperature would be at least 160. You talked about 120 to 160 degrees.
Yeah. So 50 above ambient is the minimum temperature that the fire damper must activate at, not to exceed 160. So in a typical room that's, 70 degrees, let's say plus 50 is 120, is the minimum damper activation temperature. But if for some reason the room was pretty hot, then 50 plus ambient could exceed 160. So 160 is the max.
Great, thank you. And then we had, when you were talking about the flex and the exceptions, does the non-flex or does the flex requirement also apply to fire partitions like it does fire barriers?
No.
Great.
So fire partitions is more lenient. So yeah, in fire partitions, you can use flex.
Great. And we
Still
had,
get the omission.
wonderful. And we had one more question come in for this section. What about offsetting ducts horizontally between shafts? In Chicago, this has generally been allowed, but it doesn't seem like there is an allowance for this in IBC.
I think there is. I don't have that information right in front of me now, but there's a graphic I know in the IBC commentary. I think you are permitted to. So I think the question is about if a duct runs through a certain number of floors and has a sort of horizontal jog and then continues all the way up with no openings at the floor of jogging, are you permitted to do that? Do you have to run a horizontal shaft, so to speak? Do you have to fire wrap it? Do you need fire dampers and things like that? I want to say IBC allows it, but requires fire and smoke dampers at the exit and entry into the shaft, so that you can have offsetting shafts, but your duct has basically left the shaft. So you need the combination fire smoke damper. It runs horizontally, above ceiling or wherever, enters a new shaft, another fire and smoke damper, and then continues up. So hopefully I answered the question. I think that's what you were asking.
I think so. That was all we had for this section for the moment. Thank you.
Okay, great. So those were all of the fire rated assemblies. And if you remember, all of those, the result was provide a fire damper. The only exception was the shafts, where it was provide a combination fire and smoke damper. Now we'll get into smoke resistance rated assemblies and talk about their requirements of whether or not you need a smoke damper. And you'll see a little bit of difference here, how it went fire wall, fire barrier, fire partition. There is no smoke wall. That's not a term that's used in the code. It goes smoke barrier, smoke partition. And then we'll talk about a third kind of special type. So any of you that work on hospitals or prisons, you might have seen a smoke barrier before or an atrium boundary. And these are used to divide floors into compartments. So one, you can see in the graphic here on the right, I pulled this from a hospital project. If you see the cross-swinging doors going in opposite directions, that's typically, but not always, but typically a sign of a smoke barrier wall. So the way hospital designs work, every floor that has patient care must be divided into at least one smoke barrier, and that completely cuts across from exterior wall to exterior wall. The reason hospitals are designed like this is because you can't evacuate patients that are in beds. You can't tell them to go run down the stairs. So the strategy in hospitals is defend in place. So it's more of a relocation than an evacuation. So what happens is if you have your floor plan split in two, take the patients on side A, where the fire was, and move them into side B. So that's why the floor plans are split, at least in half, sometimes often into multiple smoke compartments for patient evacuation. And a smoke barrier, just like with fire barriers, is more restrictive than the smoke partition, in the same way that fire barrier is more restrictive than fire partition. So, this is going to seem pretty familiar. If you penetrate a smoke barrier, provide a smoke damper. There are some exceptions, some pretty strong and common exceptions, that if your ducts are limited to one smoke compartment, then you do not need to provide a smoke damper at that barrier, at the smoke barrier. And in an I2, that's hospital occupancy in a fully ducted system. And if the area has quick response sprinklers, you can omit the smoke damper when crossing that fire barrier. So it might be hard to see because it's pretty small here on the right, but that's a smoke compartmentation plan. So there's 4 colors, 4 kind of shapes. On the bottom, kind of an orange tan shape, a green one sort of in the middle top, cyan on the right, and then pink in the upper part. So this floor plan is split into 4 compartments. So unless one of those exceptions are met, anytime a duct crosses that smoke barrier, it requires a smoke damper. Also important to note that smoke barriers are also 1-hour fire partitions. So you may also be required to provide a fire damper unless you meet one of those exceptions. And again, just the importance of terminology, smoke barrier is relatively rare. You'll see them a lot in hospital projects, but it shouldn't be used when unnecessarily, or it may cause there to be more smoke dampers than necessary. Now, a smoke partition is a little bit less stringent than a smoke barrier, and these are used to enclose rooms that are higher than normal hazard, like a storage room, a trash room, boiler and furnace. And if you're familiar with building codes, you might have seen this table below. If not, it's table 509 from the IBC, and it requires all these different types of rooms because they're an incidental hazard. If you meet these criteria, you have to provide whatever's on the right. So for example, furnace room, any piece of equipment over 400,000 BTU per hour input, it says provide 1-hour separation or provide an automatic sprinkler system. Well, most projects have sprinkler systems. So I guess that means we're good, right? We don't have to do anything. Actually, no. And this is something that gets missed quite a bit. If you read that whole chapter 509, it says that if you take the or provide sprinkler exception, then that room is a smoke partition. And so what exactly a smoke partition is, it's intended to contain the smoke and heat just long enough to activate sprinklers or smoke detectors quickly. So if you do penetrate it with an air transfer opening, then you do need to provide a smoke damper. But if you're ducted, you do not. And lastly, hospital corridor walls, they're required to limit the transfer of smoke. but they're not smoke barriers. So this is a case that I think it's missed quite a bit, where unnecessarily dampers are being provided because they assume that the corridors themselves are smoke barriers, but they're not. They're actually smoke partitions. So typically they're ducted, so they do not require the smoke damper. Now, there's, of course, a lot of special cases. One fairly common one, I said, well, you have to provide, fire dampers in all these locations and fire and smoke dampers, but we're not permitted to do that in hazardous exhaust. So what do we do? In those cases, your options are to either provide a shaft, a rated enclosure to protect the ductwork all the way to the roof or exterior, or provide a listed and labeled fire wrap for that system. So we do have more, but this is just some key takeaways from that section we just went through. Crucially important to understand what type of assembly is being penetrated. As a general rule, you need dampers for air transfer openings. The exceptions typically require the system to be ducted. Typically, if you do have a duct riser, so penetrating floors, it must run in shafts, although there are some exceptions. And then when you do penetrate a shaft, provide a combination fire and smoke damper.
So there was a comment in the Q&A about the commentary from the 2015 IMC about what constitutes as a ducted HVAC system. So it says, I'll try to read this, it's a little long. It says that a ducted HVAC system in this context does not contain flexible ducts, except where a steel duct passes through a fire barrier and then converts to flexible duct to only serve an air terminal device. In such case, the steel duct could have terminated at an air terminal device on the wall, thus extending the duct run further into the room to a ceiling air terminal device using flex duct has no effect on the integrity of the fire barrier penetration.
Now, yeah, well, the commentary says that, then, that's not, that's typically good, good advice to utilize. My understanding was a little bit different, that the issue wasn't that it's fully ducted, it's that it requires a minimum gauge 22 ductwork, in which case I don't think flex ducts meet that requirement. So that may be from the fire partition section where it says fully ducted, not the fire barrier section where it's not just fully ducted, but it's also minimum 22 gauge. So maybe we can come back to that if we have some time there at the end.
Thanks.
But I do appreciate all the feedback. Certainly not saying you're incorrect by any means. Okay, back to some fun. We've got some polls coming up, some rapid fire. So just real quickly, we kind of went over this at the beginning, but how does the smoke damper work? So either on loss of power or an alarm signal from the smoke detector mounted 5 feet from the damper, typically within the duct, but you may have a air transfer opening, so it could be near the just near the opening within 5 feet. Those are required, a smoke detector somewhere within 5 feet to actuate to close the damper. An exception, which is a bit rare, is if your building has total coverage smoke detection, then you can utilize that system to activate and close the smoke damper. And then if you have the combination fire and smoke, then you follow both requirements for fire dampers and for smoke dampers. And then on to the poll question. When a fire or smoke damper closes, is the associated HVAC unit required to shut down? Simple yes, no.
We'll give you just a few more seconds.
Give me time to catch my breath, rehydrate.
Fine, I can wait longer.
No, whatever you want.
All right, it looks like we got 70% of our viewers. All right.
All right, majority are correct. No is the right answer. So that's the segue into this next section. So when are smoke detectors required in HVAC, other than what we just talked about for shutting the dampers? Well, there's three conditions. There's if your return air system exceeds 2000 CFM, provide a smoke detector. If you have multiple air handlers, the common supplier return, where 2000 CFM combined, provide a smoke detector in that return air. And then in large systems exceeding 15,000 CFM, serving multiple floors, provide the smoke detectors at each story. One important exception, though, is that if the air handling unit is incapable of spreading smoke beyond the zone of origin, then the smoke detector is not required. One classic example of that might be a gymnasium with a big rooftop unit and a big wide open gym. So let's say a fire starts in the gym and smoke starts spreading. The air handler is going to continue to provide air and return air and provide air and return air, but it's not spreading smoke throughout the building. It's just the smoke's already there. It's already in the room, and you're not spreading it anywhere else. So that's the reason why the code allows you to omit the smoke detector in that system. You could, of course, provide it, but it's not required. And there may be other cases too that are maybe not quite as straightforward as a big gymnasium. But if you do meet that section of the air handler is incapable of spreading smoke beyond the zone of origin, you can omit the smoke detector in the return air. Now, if you've worked on federal projects, government projects, NFPA 90A, it also can be adopted locally, but that's kind of the opposite. They require the smoke detector on the supply side. Still is over 2000 CFM, so it's the same cutoff. And then they also have the same requirement for return air risers greater than 15,000 CFM to provide the smoke detector at each story on the return side. So you may have a project that has both IBC and NFPA 90A, in which case you would provide smoke detectors on both the return and supply side for units exceeding 2000 CFM. So next poll question, when a duct-mounted smoke detector in an air handling unit activates, what happens?
You can initiate the general fire alarm, shut down fans of the respective AHU, close all fire and smoke dampers associated with the air handling unit, or all of the above.
Oh, is this appearing on everybody's screen, the
Oh,
poll?
yeah, sorry.
I didn't realize that till just now.
Yes, it's weird and it doesn't show on any of the panelist features. So, all right, that looks like most everybody.
Okay, well, you guys fell for the trap. All the above is not the correct answer. The correct answer is to shut down the fans. The giveaway could have been the close all fire and smoke dampers with the AHU. So when the duct mounted smoke detector inside the unit activates, shut down the fans. It initiates a supervisory, not a alarm. So supervisory means that the fire alarm control panels know something's going on. They make a really loud buzz at the panel itself. You're probably going to get an alarm on your BAS. It's going to notify the fire department, but it's not going to initiate a general building evacuation. It does not require closure of smoke or any other damper. It does not initiate the general alarm. It does not shut down other HVAC units either. The requirement is for that return air smoke detector, or if you're following 90A on the supply side, to shut down the operational capabilities, that's the actual phrasing, of the unit. So typically that means to shut down the fans. And then our final poll question, it's the last bullet here. When a fire alarm pull station, sprinkler water flow, or a smoke detector not associated with an HVAC unit initiates, do the building HVAC units shut down? I guess I'll move this off the screen.
And while people are, oh, so no one should, I don't think anyone can see the poll on your screen, just so
Oh,
you know.
they can't. Okay, I thought they
So
could.
they, oh, sorry. So it should just pop up from
Okay, cool.
mine. But while we give them a second, there was a question from earlier
Mhm,
about smoke dampers.
mhm.
Are smoke dampers required to be addressable on the fire alarm system?
Yes. I don't think they are. The smoke detector is addressable, but no, I think only in smoke control systems, which we'll talk about at the end, because oh, no, that's a really good one. I'm on the fence. I'm actually not sure.
All right. Well, that's good enough for now. I will share
Yeah.
the results
All right,
of our
you stumped me.
we'll share the results of our polling.
Cool. Well, you guys got that one right. No, we do not shut down the HVAC units when a pull station, sprinkler water flow, or smoke detector. We shut down the units when the associated, so that is the duct detector within the unit on the return side or possibly supply side, is activated. So the key takeaway here is this local control idea. So the smoke dampers they have their own smoke detector. The unit itself by the fans has its own smoke detector. That's what shuts down the unit. I mean, the chain of events may ultimately result in the main unit shutting down. If smoke gets pulled into the system and it closes the fire smoke damper, theoretically, it should stop the flow of smoke and the unit can continue to run, continue serving the rest of the building. You know, imagine a large DOAS unit serving, multiple floors of the building. You don't necessarily need to shut down the entire unit. So long as you can contain the smoke, you can continue to serve other floors. Crucially important in something like a hospital, you don't want to be shutting down your operating room air handlers because there's some smoke detected in the pantry, on the other side of the building. So think about the local control. It's only the device itself that's going to be shutting down. Other events are not going to trigger an HVAC shutdown. Some projects may choose to do that. And again, back to the static and dynamic dampers idea. If you were to specify static dampers, they would only work if you did shut down the unit when you detected smoke. So in that case, again, you don't have to shut down the unit per code requirements if the smoke dampers detector goes off. But if you specified a static smoke damper, then it wouldn't close unless you did shut down the unit. So hopefully that made sense. And then the big exception here, and the segue to this last section, is an atrium smoke control system actually might require you to take some HVAC action of either turning on the smoke exhaust fans, shutting dampers along the atrium boundary. So we will get into that section next. So when is atrium smoke control required? In atriums that are open to 3 stories or more, a atrium smoke control system is required by code. If you are working on a hospital project, an I2 occupancy, all atriums require smoke control. If you're working on an NFPA 101 project, that's often adopted by government, federal, or a local jurisdiction, then all atriums require smoke control. And the purpose of the system is to ensure tenable conditions for building occupants during evacuation. Typically, this requires the computational fluid dynamics analysis. And what we do is we take a reasonable and yet bounding worst case fire scenario in the atrium boundary based on the furnishings and the use of the space. When we model that fire to determine the heat, the carbon monoxide concentration, and the production of soot, which contributes to reduced visibility in the CFD model, while simultaneously air is being exhausted and made up. And tenability is that last bullet. If the heat, carbon monoxide, or visibility reach a certain level, an unsafe level, within the atrium boundary at any point at 6 feet above the walking surface, then the model has failed. So basically, we have to provide tenable conditions throughout the length of occupant evacuation, including a safety factor. So this graphic kind of outlines the process here. So we first look at what is our fuel. We have to assume some kind of fire, and that needs to be realistic and kind of a worst case, but also credible scenario of how the building's intended to be used. Then we determine what are our tenability criteria, like we just talked about. And then we'll look at an egress model. So that will look at all the occupants within the atrium boundary, consider factors like their mobility, their different behaviors, how aware they are of their surroundings, how quickly they'll respond to a fire, and their demographic, such as age, and run an egress model to see how long it takes for people to safely evacuate that atrium boundary. Simultaneously, that fire model we talked about with the CFD is running, and then we compare those 2 models and compare the available safe egress time, so how long conditions are tenable and safe, and compare that to the required egress time, how long it takes people to actually get out based on how many people are in there, their mobility factors and things like that, and then apply a safety factor. So as the mechanical engineer, you need to provide exhaust and makeup air. And the makeup air could be active or passive to support these tenable conditions in the space. And this can be really complex. It requires a lot of disciplines across the whole board to establish a system that actually does work and meets all of all the stakeholders' intents. So critical to coordinate with all these multiple disciplines. And this is an engineered solution. It's a performance-based design. So this very well could and probably will require shutting down of other HVAC units unassociated with but located within the atrium and then closing dampers along the atrium boundary to ensure that integrity of that boundary, so that when we do start exhausting and making up air, that we have a reasonably tight boundary and we're not spreading smoke to other spaces, and that we are able to ensure these tenable conditions throughout the occupant evacuation. And unlike these other systems where I gave you that poll question to say, hey, does a sprinkler activate or does a sprinkler shut down an HVAC unit? Well, within the atrium, the smoke detectors, sprinkler water flow, and manual control at the firefighter's smoke control panel, all of those will activate the smoke control system and initiate that whole sequence of events, possibly shutting down unrelated HVAC units and activating. You can see here on the screen, I've got just a snip of 4 roof-mounted smoke exhaust fans and a makeup air fan providing air to the base of the atrium. And then there's some, you probably can't read at the bottom, but there's some smoke curtains that drop to form one portion of the atrium boundary. And there are some doors that are on motors that open to provide additional makeup air. So some important takeaways on the atrium smoke control is that the boundary definition itself can have a really significant impact. And it's arbitrary where we determine the atrium boundary to be. It can really affect the tenability criteria because there can be more occupants in the space. If the atrium is kind of long and winding, there can be some difficulty with some air and stagnant pockets that it can be difficult to actually continue to exhaust the smoke while making up fresh air. So if possible, it's best to keep the atrium boundary tight and tall so that there is a pocket for the smoke to collect in before it starts to descend and become a hazard to occupants. Then finally, just to wrap everything up, again, I'll just reiterate that it's really important to know what type of assembly is being penetrated to know whether or not you need a fire, a smoke, or a combination fire smoke damper. And if you don't know the difference between the types, you might just be guessing. You may end up over-specifying, you may end up under-specifying, and could be in a really dangerous situation with life safety. So I strongly encourage you to get familiar with IBC section 717. That's also cross-listed in the IMC, but that's the section on ducts and air transfer openings. And remember the local detection typically for HVAC shutdown and fire or smoke damper. It's by the local and associated smoke detector, not the general alarm. And then if you do work on an atrium project, it's complex, and be sure to coordinate with all the other disciplines throughout design and all the way through construction, because it is a very complicated design. So that is all I had for you today. And